In this video, I'm going to be talking about some special trig limits. Okay, these are generally included in most Calculus 1 courses. I didn't include it in my AP Calculus course because we're going to develop a trick to kind of deal with really any type of unpleasant limit that comes back 0 over 0 or infinity over infinity, and it kind of just takes care of these all in one step. But these are important in proving the rules for the derivatives of sine and cosine, okay, which I'm going to do in a separate video, but I'm just establishing these special trig limits in this video. Now, the first trig limit I've got for you is that the limit as theta approaches 0 of sine theta over theta is 1. Okay? You wouldn't think that because sine goes to 0, theta goes to 0, but they go to 0 in a very similar way. If you graph y equals sine theta and y equals theta, or y equals sine x and y equals x in the same window, you'll see that they look very similar around x equals 0. So in some sense, they behave the same. So, maybe it wouldn't be surprising that their ratio would be 1 if they were the same. Okay? So I'm going to start with the kind of this figure here. This is the unit circle, right? You see it's part of a circle and a couple of triangles that I drew in around it. And so we're going to label the coordinates of each of the points. The coordinates of A are cosine theta and sine theta. The coordinates of B, well, the x coordinate is 1, and the y coordinate, if you think about it, is going to be tangent theta. So I'll pause for a second. And if you're having trouble seeing why the y coordinate of B is tangent theta, pull out the whole triangle, the triangle DBC, and label the horizontal leg 1, label the angle theta, and think about what is tangent theta. Tangent theta is going to be BC divided by CD. So, if you think about it, that means BC has to be tangent theta, okay? Because CD, length CD is 1. Okay, point C is x equals 1 and y equals 0, and point D is 0, 0. It's the origin. Now I'm going to ask you to consider triangle DAC, piece of pizza DAC, also known as sector DAC. Okay, I'll call it sector DAC. But if I said sector, you might not know what I was talking about. I'm talking about the little piece of pizza, the thing that includes that extra little sliver of area. And then also I'm going to ask you to consider triangle DBC. Now, obviously, kind of the point I'm trying to make is that triangle DBC is the biggest in terms of area. Then the piece of pizza is smaller than that, but the smallest of all is triangle DAC. All right, I wrote in the areas of each of these things, but I'll go through them one by one. The area of triangle DAC is 1/2 base times height. Well, the base is 1 because it goes all the way, to C, which has the coordinates 1, 0. And the height is going to be really the y coordinate of A, which is sine theta. So it's 1/2 times 1 times sine theta. Now, the area of the piece of pizza DAC, sector DAC, is something, it's a formula you learned in geometry and probably have forgotten between then and now, but it's 1/2 r squared theta, if theta's in radians. If theta is in degrees, it's theta divided by 360. It's like the proportion of the triangle, of the circle that you have. Okay? Now, in our case, this is a unit circle, meaning r squared equals 1. So I'm going to rewrite this as 1/2 theta. And then the area of triangle DBC is 1/2 times the base, which is 1, times the height, which is the y coordinate of B, is going to be tangent theta. So it's 1/2 tangent theta. And now I'm going to kind of write these in order from least to greatest, right? I was saying that the area of the interior triangle is less than the area of the piece of pizza is less than the area of the big triangle. All right, so I've got 1/2 sine theta is less than or equal to 1/2 theta is less than or equal to 1/2 tangent theta. And the reason that I said less than or equal to is in kind of in the limiting case where, point A moves closer and closer to point C. If we put point A on point C, they would all have area 0, but the inequality would still be preserved if we said less than or equal to. Okay. Now the first step is I'm going to go in and multiply all 3 sides of this inequality by 2. Okay, that was easy enough, right? I just lost all of the halves. It would be just kind of less for me to look at, right? I'm not looking at anything involving a 2 in that theorem, so I'm going to just clear that all out. And then what I'm going to do is I'm going to rewrite tangent theta as sine theta divided by cosine theta. And then what I'm going to do is I'm going to divide all three sides of this inequality by sine theta. Right? So now I have 1 is less than or equal to theta divided by sine theta, which is less than or equal to 1 over cosine theta. Right? I'm just dividing everything by sine theta. Okay. Now, this is not really what I'd set out to show. I'm looking for sine theta over theta. So what I'm going to do is I'm going to kind of flip all three sides of the inequality, or take them all to the -1 power, or take 1 over each side, and that will reverse the order of the inequality. If you think about it, 2 is less than 3 is less than 4, but if you take 1/2, 1/3, 1/4, all of a sudden 1/4 is the smallest, then 1/3, and then 1/2 is the biggest. So it's going to reverse the direction of the inequality. So I'm going to do that, and then I'll bring in a separate inequality. And now I'm going to take the limit as theta goes to 0. Okay. On the left, I see that 1, regardless of what theta is going to continue to be 1, no matter what theta is. And then on the right, as theta approaches 0, cosine of theta also approaches 1. And I've got sine theta over theta squeezed in the middle. So if I've got basically, 1 is less than or equal to the limit as theta approaches 0 of sine theta over theta. Oh, that wasn't a very good theta. I'll replace that. Is greater than or equal to 1, well then I could reasonably conclude that the limit as theta approaches 0 of sine theta over theta is equal to 1. Okay? It's really using the squeeze theorem, but the proof of that is a little beyond the scope of the course and wouldn't be all that interesting to you. This is why the limit of sine theta over theta is 1 as theta goes to 0. Next, I've got another special trig limit. This one's related. I'm going to use the limit of sine theta over theta as theta goes to 0. This is the limit of 1 minus cosine theta divided by theta, and this one's going to 0, okay? And really, the proof of this one's pretty algebraic. So I'm just going to start by rewriting the limit, and I'm going to do one of really the only couple of tricks we've got in mathematics. We can either multiply by a clever form of 1 or add a clever form of 0. I'm about to multiply by a clever form of 1. Okay, I'm going to multiply by 1 plus cosine theta over 1 plus cosine theta. And this is the conjugate of 1 minus cosine theta. So I'm going to end up with the difference of 2 squares in the top, and that will be something I can apply a trig identity to. So let's just go ahead and rewrite this. Okay, once I kind of like FOIL out all the numerator and cancel off the like terms, whatever, I'm going to end up with 1 minus cosine squared theta, and then in the denominator I'm going to have a theta and a 1 plus cosine theta. Okay, now 1 minus cosine squared theta, if you remember your trig identities, that's sine squared theta. Okay, so I'm going to make that substitution. And then what I'm going to do is I'm going to kind of break up that sine squared theta into 2 powers of sine theta, and then I'm going to break it off into 2 separate fractions. So let me do that. Okay, so now I've got 1 power of sine theta going with that theta in the denominator, and the other power of sine theta going with the 1 plus cosine theta in the denominator. Now, one of the properties of limits that I would have told you about had I been here to tell you about them was that the limit of the product is equal to the product of the limits, provided that they both exist. Okay, now we know that the limit of sine theta over theta exists, and off to the right we'll be able to see that that one exists too. So I'm going to split this limit over the product and write it as the product of 2 limits, like this. And what I'll say is that, here this first limit is the limit as theta approaches 0 of sine theta over theta. I just showed you that that's 1. But the second one, okay, we can go in and we can kind of analytically look at it. We can just try plugging in, because that should always be your first recourse when faced with the limit. Just try plugging in. Okay, this is going to be sine of 0, which is 0, divided by 1 plus the cosine of 0, which is 2. And 1 times 0 divided by 2 is going to be 0, which is what I'd set out to show.